Optical fibers. An optical fiber is a hair-thin, long strand of quality glass or quartz surrounded by a glass coating of slightly lower refractive index. It is used as guided medium for transmitting an optical signal from one place to another. Principle. Optical fibers use the principle of total internal reflection for the transmission of light signals. Here, construction is shown. Core material, this is cladding, this is buffer coating, and refractive index of core material is mu1, which is higher, and cladding has refractive index mu2, which is little less, and the buffer coating is used for protection. Here description is given: core, high quality glass with a refractive index mu1, this is core. Then cladding, a glass jacket of refractive index mu2, this one is cladding, such that mu1 is greater than mu2. And then third one is buffer coating. It is a plastic jacket to provide safety to core and cladding. Now let's see propagation of light through optical fiber. This is optical fiber. This is cladding with a low refractive index 1.48, and inside this is glass core with a high refractive index 1.52. Light ray enters. At this point, it suffers refraction, and then it suffers total internal reflection at this point, at every point. And at this point, it goes out. Here again, it suffers refraction. The same is described here. In optical fibers, propagation of light takes place due to total internal reflection. When light falls one end of the optical fiber, it gets refracted into the fiber. The refracted ray of light falls on the interface separating the fiber and the coating at an angle which is greater than the critical angle. So here necessary condition is this angle must be greater than critical angle. Here in every case, angle of incidence must be greater than critical angle so that total internal reflection occurs, and finally light passes through it. Let's see some uses. Uses of optical fibers in medical industry. Because of its extremely thin and flexible nature, it is used in various instruments to view internal body parts by inserting into hollow spaces in the body. In communication, in the communication system, optical fiber cables are used for transmitting and receiving data with speed and accuracy. In a photometric sensor for measuring blood flow in the heart, optical fibers are used in the form of refractometers to measure the refractive indices of liquids. Now, let's see one question. Figure shows a cross section of a light pipe made of glass fiber of refractive index 1.68. The outer covering of the pipe is made of material of refractive index 1.44. Here it is 1.44 outside, and inside it is 1.52. Sorry, 1.68. Now, what is the range of angles of incident rays with the axis of the pipe for which total reflection inside the pipe takes place as shown in the figure? So let's find out the range of I for which total internal reflection takes place. So first of all, we have to find out this angle, and at this point, this angle must be greater than the critical angle for the interface. Only then total internal reflection will take place. So first of all, we will try to find out this angle. Then as the sum of this R and I1 is 90 degree, from there we will try to get R, and then we will try to use Snell's law at this point to find I. So let's see how. So we are given certain information that we can make use. So we are given mu2 is 1.68. Here we are taking this as mu2 inside, and this is mu1. And mu1 equal to 1.44. Now we find relative refractive index. So mu equal to mu2 divided by mu1, which will be equal to 1 upon sine I1. Now, sine I1 equal to mu2 upon mu1, mu2 upon mu1. So we can invert the value. So that will be equal to 1.44 divided by 1.68, which will be equal to 0.8571. We are given in the question sine inverse 0.8571 equal to 59 degree. Sine inverse 0.8571 equal to 59 degree. So we can say I1 equal to 59 degree. Now I1 plus R must be 90 degree. So from there we get R equal to 31 degree. Now, if R exceeds this value, in that case, value of I1 will be less, and hence total internal reflection will not occur. So this is R max, we can say, maximum value of R. Now, we apply Snell's law at this point. So we consider maximum value of I. So we can relate sine I max divided by sine R max equal to the refractive index of the inner material, that is 1.68. Now, sine I max equal to 1.68 into sine R max, that is sine 31 degree. We are also provided sine 31, which is 0.515. We are given sine 31 degree, which is 0.515. So if we put this value here, so we will get sine I max equal to 0.8662. And if you remember, root 3 by 2 is the same value. So we can say sine I max equal to 0.8662, which is root 3 by 2 for I max equal to 60 degree. So maximum value of angle of incidence at this point should be 60 degree. Hence, we can say the range will be from 0 to I to 60 degree. If this angle is lying between 0 to 60 degree, then total internal reflection will occur. Thank you for watching.